Very good. Thank you very much for coming. It's the first of this series of seminars. And we have today Eric Bergshoef that is going to give a talk about advance in non-relativistic quantum gravity. Thank you very much for coming and enjoy.
I can take this off.
Yeah, I don't know how it works. I'm going to open this just in case to make it more.
So, first of all, I would like a bit to excuse myself. It's a bit of this plan. So, I was, my seminar was planned during the workshop, but I didn't realize that. So, I'm very grateful that it somehow could all be accommodated, but I feel a bit, don't want to impose anything into the event. And I also, especially since it's also being talked about non-relativistic. I can imagine that some of you get a bit too much of it in a too short of time, but I will say a few different things than Niels does. But I should already warn you that part of my talk will be a cube, a bronze cube, and will be the Dutch project, so I cannot avoid it. Because, but for the rest, I will really talk about the different issues. I think there's sufficient differences that Niels as well. So I will talk about advances in non-relativistic quantum gravity, and the work I did is the most recent work is published in 2 papers. And it's done in collaboration with 2 PhD students of mine, Dr. Johannes Langsteiner and Chai Schulzek, and a postdoc Luca Romano, and my old-time collaborator, Don Rosil, who is now in Vienna. And as I said, I cannot avoid the Bronstein cube because it's nice to set the settings of this talk. So is that a pointer?
Let me see if I can find something.
Well, let's see. So that will work. Okay, I will. Yeah. Okay. So the idea is that you start with classical mechanics, and then you can extend it to 3 different ways by introducing 1 of 3 constants, velocity by C, or the constant H bar. You quantize this into special relativity, and then the Gn into gravity. So if you introduce C, you go from classical mechanics to special relativity. If you introduce G, you go from classical mechanics to gravity without non-relativistic gravity without relativity. That's what we call Newtonian gravity. And if you quantize, you get quantum mechanics. And then in the other vertices, you have theories which combine 2 of these constants of nature. So for instance, in relativity, you combine both Newton's constant with the velocity of light. And in quantum field theory, you combine H bar with the velocity of light. And if you do that, then you see that the most difficult one is the one that contains all 3 constants making it quantum gravity. And the usual approach is that we either try to add gravity to quantum field theory, so we add Newton's constant according to this way, or we try to quantize relativity, we try to add H bar to relativity. And logically speaking, there is also a third approach to quantum gravity to try to approach from. The question is this vertex correspond to a well-defined theory, which I will call a non-relativistic quantum gravity, and can you then go from here to here by increasing relativity, the velocity of light c? And well, that's the question I would like to discuss. And yeah, but so is there something which is mean to non-relativistic quantum gravity? I think this is an interesting question in the sense that it lets you ask several questions. Because you want to ask yourself, if you try to quantize gravity, does it only work for relativity, or can you also do without relativity? So does it require relativity? So if you don't succeed, then at least we would like to understand if it doesn't work, then is it true that you really need relativity? That's some crucial point. That's the reason that it doesn't work. And of course, there are several approaches to quantum gravity and similar to non-relativistic quantum gravity. Now we do the string theory approach. There are also other approaches. For each of them, you can ask yourself how does it go in non-relativistic way. But I will concentrate really on non-relativistic string theory. Can you give a consistent definition of non-relativistic string theory that would give a definition meaning to this non-relativistic quantum gravity? And if that would work, can you also, is there in some sense, would you say that even non-relativistic gravity requires a holograph description? Is there some holographic principle associates non-relativistic gravity by itself, independent of the relativistic case? It's a very difficult question. I will not answer it today, but it's just interesting to ask yourself this question. So I should also say that there's of course much work done in this field, and I give you a few references. I will not give too many references to the talk. So I will approach this non-relativistic thing by taking limits, non-relativistic limits. But you also can construct non-relativistic theories by null reductions, and there's a lot of work here. I will not do that, although I will, at the end of the talk, in fact, show that, and that is also known, but I will detail it a bit, that there is a strong relation between null reductions and taking limits. And I will come back to that at the end of the talk. But I will start with taking limits. And I should also say that I only take the target space, the transfers to the string, the target space is non-relativistic, but the little sheet is relativistic. If you take that non-relativistic, do that, also have it in the talk yesterday, that's a whole different ballgame that I will not discuss. If you take it relativistic, you can do the usual calculations. That's why it's nice to keep it like that. It's more conventional. And well, that is basically it. So we are ready to start. So what I will do is that I will give a clear definition of how to take a non-relativistic limit, how to do this precisely, because there's some confusion about that in the literature. And then I will shortly remind you what the sigma model is, the type of non-relativistic theory, but take the limit of the polygon sigma model. And then I will discuss these two recent papers I wrote. I will first show you that was we did the kind of target space approach. You ask yourself, can you also immediately understand the target space description of a string theory non-relativistic by taking the limit of universal gravity? That's the concept to all string theory. Sometimes also called the non-relativistic method. Can you immediately take the limit? It turns out to be non-trivial, but you can do it. There are several surprises. And once you succeed in that, you can resist and also do the supersymmetric case. And that leads to even more surprises. It's not always an easy thing to do, to take these limits. There are all kinds of problems you have to solve, but it works. And then, as a special issue, I will discuss a little bit about T-duality, the non-relativistic case, and then I will come back also to null reductions and their relation to limits. And then I'll give some output of things to do. So first, the non-relativistic limits. So what you do is, if you want to take a non-relativistic limit, in this case I take the relativity, I take the V-by formula, the head, A hat means it's relativistic. You first rewrite the fields in a different way and split the flat index into a time and a spatial direction. This defines the clocks and the rulers. And I express them here, you can see them in other fields with a contraction parameter omega. But what is important is that this is an invertible redefinition, because so first of all, if I keep omega finite, this is just a redefinition. This is still relativistic. There's nothing non-relativistic about it. I've just made a redefinition. But if I want to define a sensible limit, I require this redefinition to be invertible. So the fields at the right hand side are the fields that will become the Newton-Cartan fields after taking the limit. Now it's just a redefinition. After taking the limit, the fields at the right hand side will become non-relativistic fields. And in order to do the calculation, in order to calculate the transformation response of these non-relativistic fields, I have to invert this thing, otherwise you can't do it. And then once I've done it, I just substitute the expression I want to take the limit of, and take the limit over to infinity, and then usually the problem really starts because it leads usually to divergences. And that's the whole problem with the limits. Somehow you think it's easy, but there are always limits and divergences, and you have to take care of them. And in fact, the kind of limit I take here. For instance, you see already here that in this V-line, if you take omega to infinity, this blows up. So that's kind of funny, but it's okay. It means, well, first of all, I only want certain things to remain finite, like an action or in place of motion. So I don't care that this is infinite. It also expresses the fact that I take a non-trivial limit which relates a non-degenerate geometry to a degenerate geometry. It's not just a fluid limit, because I really go to kind of Foliation geometry. That's why things blow up, and after just settled, you end up with a degenerate geometry. That's why it blows up. Otherwise, it will not happen. Things have to reorder themselves. And the kind of way these divergences here, for instance, they take care of themselves if you take, and that's the kind of limit I will discuss with strings and with particles. It's called the critical limit. And that's been discussed in many papers around here 2000, when people look to these non-commutative open strings and non-relativistic strings. Is that if you take a particle, the idea is that this term blows up in the metric. This term blows up also. I should say, sorry, I also should say that, sorry, I forgot one thing to say, is that you see, this is not what you do if you do a Torsional approximation. This is an expansion, as Niels also discussed yesterday. Because you see, usually this term is not there if you do a Torsional expansion. But then the problem is that I have now three. See, I get now too many fields. I replace one vector by two vectors. It will be not invertible. I have to include this field in order to remain the same number of fields. This field has to do with the fact that this field, the physical interpretation of this field is the is the field which corresponds to the Noether symmetries expressed in the concentration particles minus antiparticles. So it's a very sensible thing. And if you take limits, let's say, to Klein-Gordon Lagrange, you really have to couple these things to the Klein-Gordon field. It's really, you need it in order to take the limits. And I have to include it here because I want invertibility. Otherwise, I would not do this. That's the approximation, you only have this. You don't care about it. So there are two infinities, and the idea is now that if you couple this particle to geometry, then the kinetic term blows up because of this term, but you also couple the particle to a Bezzamino term, this term, and it also blows up. And the whole thing is fine-tuned, that's why it's called the critical limit, that these two terms cancel against each other. And so there is no, and then the particle couples to the remaining fields, it will become the Newton-Cartan field, and then everything is fine. We get a particle coupled to non-relativistic gravity, but there is a cancellation of the divergences. That's important because this type of cancellation will come back in later in my talk. So it's and it is related, as I said, to the fact that you really go from one geometry kind of geometry to another kind of geometry. It's not a regular limit.
So if I take the Klein-Gordon field, do I need to take the compact Klein-Gordon field? So
yeah, if you first of all, I take then a mass Klein-Gordon field. Then if you do it in a curve, usually people do these things in a flat background, but I can do this in a curve background. What happens then is the mass term blows up. There's again divergence if you do it. But the trick is now you couple the Klein-Gordon field to this M. It's a complex field, so M is the phase factor of the mass, it's not the mass gauge field. It's called it's really the central extension of the Galileo's. So the M sees the complexity of the Klein-Gordon field, so it sees the phase transformation component. That means that the derivative becomes a covariant derivative. That covariant derivative takes the gauge field, it becomes an extra kind of mass-like term within the field, and they cancel that. That's how it goes.
I couldn't do a real Klein-Gordon field.
No, you have a complex field. If you do a real thing, I was just discussing this morning with Kim, you get all kinds of different limits, like Galilean limits, the Carroll limits. Carroll has no central extension, then you get the real fields. But for the standard electrons, there are also Schrödinger equation is complex. You have to get the real field, and the M is then coupling to the phase factor of that field, and you really need it. Otherwise, you could not take the limit. So that's the point. In general, you get infinities. And so if you take the limit of geometry alone, then another infinity occurs. Is that if you take now, I take the Vierman formalism, it's a spin connection, and if you substitute down three definitions in the spin connection, then that also blows up. There's a leading divergence that corresponds to this term here. The special thing about this term, by the way, is gauge invariant. So in geometry, the moment you take a derivative of the metric, you get a Christoffel symbol. And Christoffel symbol is not gauge invariant. You can't make a derivative of the metric with gauge invariant. Here, that's really particular to these non-relativistic theories. You can take derivatives of metrics and they are gauge invariant, and that's why they play an important role in the discussion. But usually, now people reason as follows. They say, I don't like this. I don't like this divergence. I want a nice spin connection. Let's set it to 0. Now, the moment you set it to 0, then you cannot anymore take the limit in the Einstein direction because this does not follow in the direction. It's something you goes by hand. But you could take still the limit of the equations of motion. And if you do that, then so the leading divergence is cancelled. You set it to 0. The subleading term is the usual non-relativistic spin connection. Then you can take the limit in the Einstein equations, and you get what we call the equation of Newton-Cartan gravity. And that's a reparameterization, reformulation of Newtonian gravity. This contains much more fields than Newtonian gravity because it's felt in much more frames. But if you gauge fix, you go to only the frame of constant acceleration, like Newtonian gravity. It turns out that one field plays a role in Newton potential, and that's hidden in the time components of this vector field. And it was in one vector field, x vector, and that's where the Newton potential is hidden. And that couples then to the particles in the neutral way. And the nice thing about this limit is that it doesn't assume anything. Usually in geometry books, people take all this Newtonian limit, but it's a combination of different things. It's not only a non-relativistic limit, they go to special frames, go to Newtonian gravity, and they often take big gravitational fields. Here, I only take non-relativistic limit, no assumptions. It's still valid in any frame and also a strong gravity field. So if ever I would write a book on geometry, this is much more pedagogically nice way of doing it. You should not combine two things separately. It's much nicer. But nobody does that. Now, now this is that I couldn't avoid it. The point is that so people they quickly set this torsion to 0, and they like it because if you set this equal to 0, then the clock function becomes a total derivative. And that means if you calculate, so this represents the universe, and each slice of bread contains all events at a given time. And now get really this makes this space-time in the Newtonian space-time, gives you the notion of absolute time, because this is a total derivative. If you now observe go from one slice of bread to another slice of bread by two different paths, then the integral is independent of the path. It only depends on the endpoints because of this total derivative. And that means that's the definition of absolute time. So that's why people like this. They say, oh, well, we live in Newtonian space-time, so let's do it. I should also say that if you don't do it, and I will not do it later, because I will try to avoid this. The theory will tell what the constraints are, but then you get what is called torsional Newton-Cartan gravity. And if you take the method postulate for tau, you immediately say that the understand part of the Christoffel symbol contains now this d tau. So this is what you call intrinsic torsion. It's not a separate torsion tensor, it's part of the metric. So some parts of the Christoffel symbol will be what we call intrinsic torsion. If you don't set this to 0. But as I said, usually people set it to 0 because they like the Newtonian space-time. Now, I want to do now something else because I'm not interested in particles, but I'm interested in strings. Now, the solid particle is a cancellation divergence in kinetic Newton. The problem with this story is that this Newton is made for particles because it had a vector, and only vectors couple into particles. Now I want to do the same thing with string, so I can't do it with particles. I have to replace that vector by a 2 form, and then do the same trick. So, and that's where the Coulomb-Field becomes important. So I introduce a 2 form just because I want to cancel the divergence of the kinetic term in a sigmoid approach. And this, the thing is going to cancel the divergence of the kinetic term, and this is then the non-relativistic Coulomb-Field. And this term I cannot write down unless I use 2 taus, otherwise it's identically 0 because B is antisymmetric. So I replace a single tau by 2 taus, and that has to do with the fact that we go from a codimension 1 foliation to codimension 2 foliation, because now 2 directions are special. From particle, the time direction is special, but from string, the time and also the direction along the string is important, is different. And the rest are called transverse directions. I have 2 longitudinal directions and 8 transverse directions. So that's why we call it the codimension 2 foliation. So I split now my indices, flat indices, in an A and A prime, where A is the 0, 1 longitudinal, A prime is the transverse directions. So that's one extension I have to do from Newton-Cartan gravity. And then the basic variables I'm going to use are these. So for the particle, if I want to construct Newton-Cartan gravity, I replace my V by and this extra vector field into a clock function, a ruler, and this extra mass vector field. And what I do now is that I, in the case of string, where I couple to the inversion of gravity, I have 4 by and call more filtron. I replace by tau, the 2 taus, and so the transverse east, and now a non-relativistic Coulomb and a 5. Now, note that I omit the M. So, in other words, I replace the M by B. In our early papers, we made an unfortunate complication because what we did is that we first took the limit of relativity, where we kept the M, and afterwards we added the B, including the B mu. So in our early papers, it is both M and B. That's not right because that's too many. The thing is not revertible. Get unnecessary sugar formulations is completely unnecessary, complicated. Don't do it. So I don't extend the B mu, I replace M by B. Then this is again invertible, I not increase more field, and everything is nice. No sugar there. It's just not necessary. And then but the Newton potential is hidden in the time component of M. So where is the Newton potential? Well, now it is in the longitudinal components of the B mu. So this is something, for instance, already you need now doing quantum gravity. If you, let's say, if you see a cosmic string in the universe and you have to couple non-relativistic gravity to the cosmic string, you could ask yourself how, with the usual formulation, how could I couple the Newton potential to the cosmic string? Because the Newton potential is in part of a vector, and the vector cannot couple to the cosmic string. And the idea is that you really, that is then best described by this formulation by using 2 form, and the Newton potential is hidden in 2 form. So it's a very natural extension of Newton-Cartan. And they are not unrelated because if I can also do a reduction over the extra foliation, go from string to particles, and then you get connections. So it's not that it is a complete new thing. So that's what I will use. And now I'm ready because now I can make the signal model. I will give it to you. So that's what you did in recent work with Darwin Gomez and Young. Many years ago, as Niels already mentioned yesterday, there was this papers by these people here. They constructed around 2000 the non-relativistic flat background, and we identified the curved background, and this is the answer. So We have the spatial v-bindings decoupled just to the kinetic term. The norm is called a more various Newton term. Is a term also revealed over the dimension here. And the funny thing now is that the relativity metric that is special is replaced by the pullback of the longitudinal v-binding. So there's no, I will explain in a minute, but that has been gone and it is now replaced by this. And this is the proper generalization of subspace time to a stream to the background. And the way you take the limit is a cancellation of infinities. So there is no need to impose any geometric constraint. Now, and this is already a puzzle because I just told you when I took the limit of relativity, I imposed a zero torsion constraint. So how did I avoid that? That I'll explain in a minute. But that's the subtlety. But in the sigma model, this works. Now there are several remarks to make about this sigma model. So that's the starting point of our investigation. One is that I omitted to say that there is an extra term containing two Lagrange multiplied fields. And I've integrated them out because then I get a nice sigma model. But the result is if you integrate out is exactly that you can solve the metric of the relationship in terms of this. So this relation is the result of integrating out Lagrange multipliers. But I really should not do it. I just did it not to complicate things. If you do, let's say, a beta function calculation, you have to keep the Lagrange multipliers, and they will play a role in the story at some point. So just remind you that I just omitted this. Another thing is that if you do all these redefinitions, you end up with the Calpin field starts to play a very special role. Namely, it's not just a gauge field, but it also transforms into the boost. So remember, the ansatz for the 2-4 also is blown up. So again, it is a heavy limit, but at the end, if it just goes up, the whole geometry is so beamless, it becomes part of the geometry, it transforms into boost. So it's not only the metric is part of the geometry, the beam will really become part of the geometry, and it's really needed also to make something about sigma invariant and the boost transformations. So that's a very curious thing. It's really, so it's important that I do not look to generativity alone as we've seen, but generativity plus method. That the whole thing is only nice, not only generativity. Then another very important point. I'm going to say a very important point. So
I saw you were in the other room. I've been waiting for you to show up.
I should wait.
I thought I was the only person.
I know I wrote down that. But anyhow, I didn't say that much. So now what's an important point is that it turns out that this sigma model I give has an unexpected emergent anisotropic notation. Namely, if you vary the longitudinal v-binding and the dilaton, then the whole thing is a very net combination. That has a very funny effect because it means that the sigma model doesn't see one field because this is kind of stupid symmetry. So you miss. So you start in a relativistic field, couples to all the non-relativistic universal Lorentz fields, but after you take the limit, the number of non-relativistic background fields is one less than the relativistic ones. That also means that there's one field missing, so you can never get it by beta function calculation in your target space action. So my target space action contains one less field and hence also one less equation of motion. So that's very funny. So something is happening here, and we have to think about it. But that's just for the moment of observation, and will play a very important role in forming this emergent. And it's anisotropic, it's only the south, not the east. Now, okay, that's why I'm rather short with the second role, but I don't want to talk about too much of units yesterday. But now I'm going to talk about the first of these two papers we wrote, because we asked ourselves the question, okay, we can take the limit in the sigma model. So can we now, instead of doing the beta function calculation, which was already done by several people, can we immediately take the limit in the relativistic Divergences action, and can solve the puzzle that I just explained? And if you take the limit only in relativity, the connections blow up, and then we impose constraints in order to avoid divergence. But we don't want to impose constraints because the signal didn't require imposed constraints. So how does it go? Well, the answer is that again, that you should not look to generativity alone, but you should look to the whole universal gravity system. And there is not only an Einstein-Hilbert term in that action, but also a Calpin kinetic term. And if you do now this redefinition, so if E blows up, that means the Einstein-Hilbert blows up. But the B also blows up because in the second model it was supposed to cancel the kinetic term divergence by this. But this is also an infinity in the kinetic term of the Calpin field. So if you do the expansion without taking the limit, then you can expand S in terms of quadratic in omega, this is 0, or then omega is the one you're interested in, and this goes to 0, omega goes to infinity. Omega is the contraction parameter. And this thing is now, like in the this is now proportional to distortion transfer, but I have now 2 tau's. So, but I'm not going to say now that this is 0, that's what we did in the past, then we get a constraint. No, now the miracle happens because it turns out that the divergence coming from this term is proportional to this. The divergence of this term is also that form, and they exactly cancel. In fact, it really, in hindsight, it exactly repeats the cancellation of the divergence in the second model. It only happens on the target space actually. It's a very natural thing in some sense, but this we didn't realize in our earlier papers, and then we unnecessarily impose this constraint, but you don't have to do it. Cancels, no constraint. And the second thing is that's also not completely obvious, but if you take the limit now, we check that this S0 is invariant on this emergent, unrestricted local dilatation defined in the model. So there's an extra local dilatation variance. So let me make a few remarks about this action. So this is the action defined. Let me just briefly say there's a kind of Einstein term for spatial rotations. You see now some torsion terms, because remember I could take derivatives of metrics and Gates invariant, so you expect torsion terms. P is a kind of dependent Gates for dilatations, and H is the curvature of the Kahl-Ramon field. You see only the transverse Kahl-Ramon field occurs, the other Kahl-Ramon curvatures, they are hidden in these spin connections, because as I told you, the Kahl-Ramon is part of the geometry, and to make properly transform the spin connections, I do not only the metric, I also have to add Kahl-Ramon fields for the spin connection. And only then it transforms nicely. It transforms in the boost, and I won't have to transform nicely in the boost. And so that a lot of it is hidden is one thing. The B field occurs explicitly because you cannot make the action manifestly invariant in the dilatation and Galilean boost at the same time. So that's a bit, it's just the way it is. But we check there is an emergent dilatation symmetry, and it means that there's one field missing and hence one equation of motion. And this is not what we would call conformal gravity because the B is completely dependent. So there's no special conformal transformations. It's just really a Supergravity symmetry. So I want to make it nicer. It's nice to use independent PU, and then everything is nice. But it's not like in conformal gravity where you have dilatation events without using PU. Now, but what is now the curious thing is if we miss equation of motion, what is that equation of motion? And it turns out that it is a rather important equation of motion because it's exactly the Poisson equation of the Newton potential. That's the one that is missing. But in some sense, it is well understandable that it's missing because there's a kind of folklore that if you see the Newton-Cartan gravity, if you base it on only the Barkman algebra, that's important. No other symmetries, only the Barkman algebra, then we don't know how to write down an actual Newton-Cartan gravity based on the Barkman algebra. It is not. But if the Poisson equation would follow from this action, if it happened, there would be no dilatation symmetry, then this would be a candidate action for Newton-Cartan gravity based on the Barkman algebra. But that would be too easy. It just doesn't happen. There is no action, as far as I know. And so that fits the scheme that it could not have followed. So there is an extra Poisson equation. You could say yourself, but what the hell is then the relation between the Poisson equation and this action? Well, together they form what's called a reducible, undecomposable implication. And that is always happens in these non-relativistic symmetries. Already, if you take a Galilean boost, you see, a Galilean boost is half a rotation because you have in a rotation you have space for time, time goes to space. But on a boost, you only have space for time. The time doesn't go back to space. So it's half a rotation. And that happens on several occasions. So here it also happens that if you take the field equations of this action, since this is boost invariant, under boost, they don't go to the Poisson equation. But the other way around is not true. If you want to check that the Poisson equation is the variant of the boost, then it goes to these equations of motion. So it goes back to these equations of motion. So again, it forms this kind of reducible undecomposable representation. So the definition of the Poisson equation to make a Gates variant needs the action. So it's not that there is no relation. In fact, this is a very interesting thing which you can already do with advanced mechanics. That people usually have actions and symmetries in equations of motion. But this is a kind of generalization of the concept. If you have non-relativistic symmetries, then this can happen that you have equations of motion that are related to the action, not follow the action.
Eric, quick question on your previous transparency.
Previous transparency.
This
one?
Yeah. When you say S0 is invariant on a local dilatations, that's
again.
when you say S0 is invariant on a local dilatations.
Yeah, S0 is invariant on local dilatations.
The question, that's including the dilaton kinetic term.
Yeah, that's including the that is here, the dilaton transform and the time, they're both transformed. Yeah.
That was more like because you didn't write it in the action. But you mean you mean the action plus the
Yeah. So I wrote the action because I don't want to give too much formula. Yeah, sorry. So I
sorry,
it's including the people. Yeah.
And here it sits in the B square.
What?
In this equation, where is it? Or it's just not there?
It's hidden in B over. It's hidden
there to
in
the
B square. It's kind of same thing. It becomes kind of compensating field. So it 5 tiles come together to make some implementation event. So it's hidden in this field. But there is a file, obviously.
That's trivial.
Yeah. So, and there's one more thing, because the number of equations and motions, you see, if you have an equation motion, so I have an equation motion for the Torsional, but if I have less fields, that's the same still, it remains true. If you remain the same number of equations and one less field, you get an overdetermined system. So you expect that one equation should be special. And indeed, it turns out that the equation motion of the Newton potential itself, so I should say the Torsional equation follows from the equation motion of another field, and not of diagonal. But the equation motion of Newton itself gives rise to a non-linear geometric constraint. So that's not a linear kinetic term which solves an equation, which solves for a field. So that's why you lose a field, you also lose the predictive power of one equation. This is just a constraint. And that's why you expect this to happen, because then you prevent an overdetermined set of equations. So I should say the constraints on the geometry come back by equations of motions, or alternatively by calculation of beta functions. Like the Einstein equation is also is constraint in the geometry. So it's not that you don't get any constraint, but in taking the limit doesn't require constraint. In calculating the equations of motions, you do get the constraint. And there's one of them. There are also other fields which have constraints, and you have to solve them if you want to have a solution. Now, let me compare now, because there are 3 things you can compare. All these different results. You have an action. You can take the limit of an action. You can take the limit of the equation of motion. You can take the limit. You can calculate beta functions, and they all give different answers. These beta functions have been calculated by all these people, and it should be, of course, in accordance with what we have. And due to this emergent dilatation symmetry, all of them give something different. So, if you take the limit of the action and you take the equations of motion of the non-relativistic action, you miss one equation of motion, and that's the Torsional. So you get, let's say, you get the common equations, which all these 3 approaches give, plus a non-linear equation, that was the equation of motion of Newton potential, but no Torsional. If you calculate the beta function, what these people did, they find the same common equations. They do find the Torsional equation, but they did not find the non-linear equation. It did not occur in this work. And if you take the limit, that's the best thing. If you take the limit, if you first vary action, the relativistic action, then you take the limit, then you get everything. You get common equations, Torsional, and non-linear. Because the relativistic action has no dilatation symmetry. It has an emergent symmetry after taking the limit. So if you take the equation of motion, the relativistic action, you don't miss equations of motion. But still, it is funny that the beta function just doesn't give you this non-linear constraint. But it was remarked by Jan in a recent paper that, in fact, you do need it, because you see, I ignored a bit these Lagrange multiplier terms. And what he showed is that if you do a quantum calculation, that by definition, a Lagrange multiplier is a linear action. But he showed that in quantum vector action, there was a term magnetic in these Lagrange multiplier fields, which means it's not a Lagrange multiplier anymore. And they can show that it becomes a relativistic string. So deep claims that you have to impose is sometimes it takes extra beta function. This avoids that the non-extinct theory flows to a relativistic string theory. It sets the coefficient of this possible Laplace scattering equal to 0. That's exactly the term which was our non-linear constraint. In that sense, it would fit, and then you have to impose all these things together. That's the conclusion. There is also an extra beta function. You could say this is related to Lagrange multipliers. That was explained in this paper. Now, that is nice. So the geometry based on this is, you could call it sometimes a dilatation invariant torsional string Newtonian geometry. Niels discussed already torsional string Newtonian geometry. So the basic variables are this, and there are now many spin connections and gates and dilatation gates, and all these fields are dependent. And you make them dependent by imposing constraints on these fields, what we call usually conventional constraints. So you set the curve, some curvature of tau and e to 0, because they contain these fields and they can use them to solve for these guys. You also impose constraints on the curvature of the B field, because that's part of the geometry. It's also because it contains, it's not invariant in the boost, so it contains the boost connection fields. And you can use it also to solve some of the boost connections. And that's why the solution of this spin connection contain the curvature of the coherent field. And I will not give you the details, but you can do it in this all becomes dependent. And then, if you calculate the geometric postulate of these sprouts in east, then you find that there is again torsion, and that it's similar to the relativity case. The torsion is proportional to the curvature of these sprouts. But the special thing is now that this torsion contains both the spin connection and the dilatation case, because it's all manifesting invariant dilatations. But the point is, this thing here is a combination of a geometric constraint and a conventional constraint, in the sense of it has three indices, but not every projection, if you project this mu into space and time, not every projection contains omega and b. There are certain projections where the omega and b drops out. That's like in geometry, the curl of tau here, there was no gauge field. So here the same thing happens. If omega and b survives after projection, it's a conventional constraint, and then it's your zero used to solve for this. But if you consider a projection that is not drop out, and there are certain projections, then this doesn't contain omega and b, and then that constitutes that these components constitute a really intrinsic torsion, torsional Newton-Cartan. But anyhow, this notation is very nice if you really want to write down this function in a covariant way. I won't say too much about it. How much time do I have?
20 minutes.
What?
Yeah,
20 minutes. Okay, that's good. So now let's do supersymmetry. So all the surprises that happened so far, they occur again, but are extra surprises and extra problems. First of all, we have now to learn how to take limits of fermions. But that was done already many years ago in a paper by Bowens, Caballero, and Townsend. And what you have to do is that you have to not just take the limit of fermions, but first you have to take projections of the fermions. And then, so you have to use the gamma matrix, the longitudinal gamma matrix. So you make projections. And then, if you do the redefinition, each projection scales differently. That's the trick. If you don't do that, you get really not nice answers. And if you do that, then again, you get an example of this half rotation. You get two spheres, two projections, and one spin goes to the other, but this one doesn't go back. So again, each time we have half a rotation. And these are the proper variables to work with if you take the limits, and then you can just do it. But now there are complications, and I will skip many details. But one complication is that, well, first of all, it's now not so clear. We want to take the limit immediately at the level of the particle space supergravity actually, but the relation to the sigma model is now less clear because you see to get supersymmetry there are two ways to do it, really short and very short for more. You have boundary conditions. The supersymmetry doesn't go through the out sigma model. So you're not sure. We cannot so much use of the sigma model. So we just took the limit immediately in the supergravity. But the problem is that in the bosonic case, there was a nice cancellation of divergences in the action. And it happens again in the supersymmetry case. But you see, in some sense, supersymmetry is the square root of the equation motion. There's two supersymmetry is the equation motion. And it turns out that if you take the square root of the divergences, then you don't cancel because they're different parity. You only can get these dual combinations. So you have two things cancel the action, but in the transformations, one is extra absenceable, and then you just take a dual combination. But the constraint remains. So the constraint just remains. So there is a divergence in the supersymmetry loop. So we were lost because there is a divergence. So you can't go on. So and that is during the pandemic, we already depressed, and then it just didn't work, and you don't know what to do because there's nothing you can do. But then the nice thing is that we could not believe that it would not work, because then the whole notion of a non-relativistic superstring would not exist. And then we found something very nice and very interesting. I think it's very interesting because we found that infinities that there were already in the bosonic case, we had emergent dilatation. And what we found is that there are also two emergent superconformal transformations. And it turned out that these infinities that we found exactly occur in the form of a field-dependent Supergravity transformation. In other words, the infinities occur in components of the field that do not occur in the action. So they just drop out. They are not there because we get them. And also the nice thing is that, and that's for me a big surprise, I thought that the smallest supersymmetry multiplied in 10 dimensions is the usual supergravity we all grew up with. But what we found is that there is a smaller multiplier. It's a shorter multiplier that contains less fields, because this means that the certain fields absolute. So there is a small supersymmetry multiplied in 10 dimensions. The price of the page also, but is that it's not relativistic, but it is shorter. But that was not all. But we also still have to impose. It's very subtle that we still have to impose also by hand these infinities to zero by imposing what we call a torsional constraint, following the work these people here. So we had to set a combination of this is a torsion component in the Christoffel symbol. This was given by this term. So this is an example of a derivative of a method. This doesn't engage fields. And this combination, this defines a certain foliation. We have to be equal to 0. This represents 36 difference constraint. And if you, and that's why we call it cell dual torsional geometry.
Eric,
Yeah.
the minus is like on Torsion.
That's the, of course, it's a light connotation because I have two towers and I have minus presentation. So it's the minus relation to 0. And now usually it's very, very dangerous to impose a constraint in a supersymmetry multiplier because then you also have to require that the supersymmetry variations are 0. That needs to be disaster. But it turns out that because of the scalar projections, this tau is invariant. This combination, dual combination is invariant from the supersymmetry. So this thing is invariant in supersymmetry, and you can do it. And you have to be very careful because in this supersymmetry, you have leading terms, subleading terms, and you have to be sure that subleading terms don't spoil the supersymmetry of the leading terms. So you have to be very, it's a complicated analysis we give it in the paper. But if you do this, believe me, you make use of these asymmetries and you have to impose this, you cannot avoid it. Then we showed that the whole action is invariant under given supersymmetry. But it is a shorter multiplier. And we call it a cell dual torsional geometry. So that's a funny action. We have now an action for minors, we call it minimal supergravity, but it has an emergent rotation that remains, and it has emergent, two emergent superconformal symmetries. So there's one missing bosonic and two missing fermionic equations of motion. Now, these missing equations of motion again follow if you first take if you take the limit, non-limit of the relativistic equation of motion, you get them. And what you find is again a kind of supersymmetric version of the Poisson equation, and plus two extra fermionic partners. But now the question is that how does it go now with the action and the equation of motion? Because you see in the bosonic case, I told you that the Poisson equation that was related to the action in the sense that under a boost, the Poisson equation is sort of back to the equation of motion of the action. But in supersymmetry, it's slightly different because you can't have this half rotation. In supersymmetry, also both goes to fermion, but fermion also goes to both, otherwise you never get a translation. So you can't do half rotation in supersymmetry. So you need that the Poisson equation that not only under supersymmetry the Poisson goes to the equation of motion of the action, but also that the equation of motion of the action under supersymmetry goes to the Poisson equation. It's non-multiplied. But how can it be? Because the action usually, and that's in fact a nice paper by Van Heck, if you have an action which is supersymmetric, then its own equation of motion are formed supermultiplied and are not all equations. So how can it be? Something must not work. And what doesn't work is that what we have is really, in a sense, a pseudo action, in the sense that it is only invariant in supersymmetry if after varying under supersymmetry, you have to impose this constraint, you have to set it to 0. It's likely to be supergravity, so there's all to do with pseudo action. It has to have this funny property, because if it would not have, then according to Van Heck and Van Groningen, then the Poisson would not talk together. But because it's not really a true action, it's a pseudo action, then we found that all equations of motion for one supermultiplied, and they all transform to 0. So, and the technical derivation you can find in our paper, I will not say too much about it, but so in that sense, it is a pseudo action.
What is the supersymmetry algebra? What is the supersymmetry algebra? Non-relativistic.
Well, just well, we calculate the commentators and the closures, but there are two supersymmetries which have epsilon plus and epsilon minus. But usually, of course, the leading part is two supersymmetries with translation, but then plus more symmetries. So it is something which I do not make a very nice thing. It's close. That's important.
This may be related to this Supergravity algebra that we did with Paul, where also we are having one of the supersymmetries was producing the momenta, and other one were related to some sort of central extension or something like that.
Yeah, you see, the problem is that I don't have Bartman because I have no value. You see, the problem is that I have two-form field. And then for me, it's difficult to think about algebras. Niels had some proposal yesterday of how to relate two forms to algebras by replacing the two vectors. But I'm not sure that you can do it also in a supersymmetric context, because then I really have to reformulate supergravity. The question is, can I replace the two form by two vectors in a supersymmetric algebra? I don't know. But you see, sometimes that's although I wrote papers about algebras, I forgot now about algebras because I had a few algebra closures and I can't immediately quickly relate that. But sometimes I don't need answer fast. I have what I have. It's a field theory, all the closest, and I'm a happy man. So I don't know exactly, but certainly it's not just an ordinary bark.
The people of Torino have reformulated Philip Ferris-Alader as Aliader for.
But the same question is in all data supergravity. People ask themselves how is 2 form, 3 form, 4 related. Niels mentioned old work also by the Torino people. My whole life I've tried to understand the 3 differential algebras, but I never got to keep in peace with it in the sense of that, this might work. So I don't know. For me, it remains a bit difficult thing, but I know there are attempts and proposals to do it, but I don't know too much about it. So, but in some sense, why should I relate? I have everything already. I took the limit, I have an action, I replace motions, the physics there. Why should I now try to
have some synergies, these natural,
if there would be an answer, I would do it, but I do not know the easy answer from this supersymmetric. Okay. So I do not have a clear answer. I do know that the commentator also are close. But if there would be a nice one, I would give it.
So how do the boost how do the supersymmetric transformations, the non-relativistic ones, transform out of stringent Galilean boost?
Well, I wrote already how the fermions transforms in the boost. Then we epsilon, so epsilon plus goes to epsilon minus, epsilon minus just go back to epsilon plus, like all the other fermions. Because like this, so all fermions transform that way.
Just to say, I'm not an expert.
What?
I'm not an expert, but I think there must exist a supersymmetric realization of the stringent pointer. It must exist.
Well, of this stringy, what do you mean by stringy? Well, we
call that the stringent pointer because it gives the NS effect.
But for me, then the question became consistent. It could be that in supergravity, is a formulation supergravity where you replace the Kalpamon form by 2 vectors and close the algebra on each of these 2 vectors. That's definitely correct. If you could do that, then but I have not seen such a formulation. But that would for me be the question. If that's possible, then okay. But I have nothing to add, so I really.
One has to define.
Okay. So I want to end now with making some remarks on T-duality, and I have not much time now. 10 minutes. 12? Oh. So let me go. First, this is kind of standard thing that if you have a relativistic string system model, then there's one way to introduce T-duality is by doing duality transformation on the world sheet. We pick a direction y, that is in spatial killing direction, they put the adapted coordinates, and then you dual y by adding this term here, you go to dual coordinates. And this is Lagrange multiplier v is equal to the Bianchi identity for y. And then there are 2 ways to eliminate. Either you get one, you go back to the original formulation, or if you impose this equation motion, solve v in terms of the dual coordinates, and then get a dual sigma model where basically the metric is basically divided by one of the metric, and r goes to 1 over r duality. That's the standard way to do duality in the relativistic case. If you do this for our non-relativistic sigma model, then you can do it again. Now, there are now 2 ways. I could do it in the longitudinal direction or the transverse direction. If you do it in the transverse direction, you get the usual cushion. It's nothing much change. But in the Z, if you do it in the longitudinal direction, it's special. And the reason that it's special is that, remember, the sigma model contains extra Lagrange multiplier terms that come only to the longitudinal state. So it matters if you visualize in the longitudinal direction, these Lagrange multipliers are important. And if you do that distinct, then you can again solve for the Lagrange multiplier in terms of the dual coordinates, but you also solve it in terms of the Lagrange multipliers. And if you then substitute that, you get terms in these Lagrange, and they are not Lagrange multipliers anymore. And so in other words, what happens is that you get a kind of, it looks like a relativistic system model. And that is well known that you get then, if you do a duality in the longitudinal direction, you get back to the original model. It looks like now a polygon model, it's pure relativistic, but the funny thing is that it has in this Z direction, there's a null direction, it's a like direction. So really it's not relativistic because this breaks the relativistic symmetry. It's not a relativistic theory, it's really a way to define a non-relativistic string theory, and this is also the approach in work by Niels and collaborators to make the non-relativistic symbols like that. So the longitudinal spatial T-duality of the non-relativistic string is the pointer string moving in the arbiter with a like direction, but that together is non-relativistic. Now now comes an interesting thing, because if you want, it's a start remark, but I would basically do the bosonic case, but you think about it, that how would that go in the symmetric case? Because this is a constraint. This removes one to the Klein scale. And it's very dangerous if you have a supergravity multiplet, it's already we think it's irreducible. And if you then impose constraint, then that's usually it's a disaster. You get everything to zero. But note that this constraint again breaks the relativistic symmetries. And what is nice, it's not yet published, but that it seems to work, because if you vary this thing under so this thing is some sort of the T-dual version of the local dilatation symmetry at the other T-dual side. And then you find as a consequence that some component of the gravitational is zero, and this stands for the two superconformal Supergravity symmetries we have. And then, if you vary that, then you get this stands in some sense for this foliation constraint we have. That in this null reduction ansatz, you have to now use a null parameterization, that this particular component is also zero, and it is extra right to 36 constraint. But this thing, it's plus means that there's a combination of the spin connection and the Coulomb curvature, that it only transforms back to psi z, then psi z to close. So it closes. So in other words, this is kind of T-dual way of saying that there is a short multiplet. So if you have a supergravity multiplet, you say k squared is zero, then you get a shorter multiplet. And these are exactly the things you remove. So this is a kind of T-dual of saying that there is a shorter multiplet in 10 dimensions. And that's kind of interesting. I was not aware of that. And as I said, if you T-dualize in the transverse direction, then the Lagrange replies don't play any role. The remaining Lagrange replies and just get pushy rules in the transverse direction. Now, I'm getting there. So I want to make one more remark. Yeah, no, now in the relativistic case, when we were young, together with Chris Holton, we did also in a kind of target space point of view of this T-duality. But let's say, take for instance 2A to B supergravity. The statement is just that 2A and 2B are the same, provided you reduce them over a spatial direction to 9 dimensions. There's one 9-dimensional theory, and if you reduce this over a circle of radius R, if you circle radius 1 over R, you get the same thing. So this establishes an identification to 2A and 2B, provided you have a spatial killing vector. So the spatial reduction to A is the same as the spatial reduction to B, provided you reduce it to dual. This is a very nice description of T-duality if you want to extend it including fermions and Ramon morphisms. But if you want to derive this from a sigma model, it's complicated. That's done, but it's really nice to use it for extensions to include symmetry, Ramon morphisms, geometries. And that's why we also did this for the non-relativistic case. So then the target space point of view is that we have here this limit of this string Newton-Cartan gravity, this limit of universal gravity. And if I do a long T-duality, I get, let's say, the relativistic universal gravity with a null direction. And the idea is now that if you do here a reduction of the spatial foliation, because you want to go from codimension 2 foliation to codimension 1 foliation, so you do a longitudinal spatial reduction. And if you do here the null reduction, you get the same non-dimensional standard Newton-Cartan gravity for particles with a one-dimensional profile. And now you can nicely see how it works in practice, because you see, if you do a spatial reduction, here you include Klein reduction. Here I have the basic fields of steering Newton-Cartan gravity, and you have to do some fixing in the Galilean boost. But then you'll see that's the important point, is that if you do the ansatz, the Klein ansatz, there are 3 vectors. One from the metric, then another from the metric, because there were two longitudinal metrics, there are 2 metrics, and one from the Coulomb. There's 3 vectors. But from this side, if you make an ansatz for the null, this was also discussed in the talk by Niels yesterday, then you split the mu into a 9-dimensional curved index and z as the null direction, but the flat index you split into 8 transverse and then a minus and a plus. It also gives you 2 vectors. And then the vector coming from B. And then you can see that the T-duality is nothing else than that you say that the B from the Coulomb here should be identified with the N coming from the metric here, that the A from the metric here should be identified with the B from the Coulomb. So it's just an interchange of vector coming from the metric and Coulomb. And in the relativistic case, you say that's an interchange of binding and momentum poles. And that's so here it's exactly the same thing, just interchange. It's a C2 symmetry from the 9-dimensional point. And it's nice, that's the last remark I want to say, is that now you can also compare this null reduction. You can understand now that the null reduction in some sense is also can be obtained from a limiting procedure. Because what you could do, you could say, let's take the string Newton before I take the limit. I don't take the redefinition. I don't yet take the limit. But now take the T-dual of that redefinition. And the funny thing is that if you do that, you get exactly at the T-dual side an almost null reduction ansatz, but the omega has not yet been to infinity. And if you then, and before you take the limit, in fact, this thing, which will become soon a null reduction ansatz, is nothing else than a spatial reduction if up to a boost, and you have to go from Lightning coordinates to time and space coordinates. And that's well known when people did the Lightning conversation, that a null reduction is nothing else than a spatial reduction involved by the infinite boost. It's the same thing, and you can see it here. For over finite, you can realize this, it is really equivalent to a spatial reduction. And once you take over to infinity, it becomes a null reduction, and it is the same null reduction which was used at the right side of the triangle, provided again to identify the vector from the matrix with the vector coming from the Kalpomon field. And then, so in that sense, it's literally, you do literally the same thing, but you just interchange the TSNC. That's what T-duality is. And we are using this now to extend our T-duality rules to include fermions, Ramon fields, Young-Mills, etc. So, and we like that because then we can also look at solutions. Now, this is the end, but there are now many things to do. So let me stress them. First of all, this limit technique we did, how general it is. Well, you want an invertible field definition, is important. You want cancellation divergences. Dus that can also happen for vectors, because I use now 2 forms, but yes, you can, my point models that cancels. But what is not clear is that you get this emergent anisotropic dilatation symmetry. So it's not guaranteed that you get it's something related to the Newton-Cartan galaxy. So I don't know the answer to that, but I'm sure there is a more general way of seeing when you can take this limit, as I discussed in the bosonic case, but how general it is and for which P-form fields and when you get low interpretations, would be interesting to find out. Then our wish is to include now the Ramon fields, also by the S-duality, it's also important. That also make, I didn't discuss it, but we have to really think about what's the opening point, what is non-perturbative in this case, because there are funny things going on with the mode-like parameters. So this is a non-trivial issue to find out what S-duality is, but we are working on it. One annoying thing is that we clearly want to extend our nerve function to include Yang-Mills, and we can indeed take the limit of flat Yang-Mills, that's no problem. But if you couple to gravity, you get these transscience terms, the Yang-Mills transscience terms, that leads to other cancellations which should happen, and so far you don't cancel. And it's a bit annoying, and we need some time. I can't believe again that it doesn't work, but it is slightly what it looks like. That's what the indication you have is that that's very funny. You have also to if you do the redefinition, some of the gravity fields have to be expressed also in terms containing the Yang-Mills field. That somehow seems to be necessary to avoid infinities. But we have not yet worked out. It's also here, of course, now. Oh, the sigma model is extra complicated because we know that this transscience term is based on a sigma model anomaly. So it's not the relation to what you do at the sigma model level, the type space level is not so straightforward because you wonder then how does that go with the sigma model anomaly in the non-relativistic case. So that's something that we're still working on. Obviously, we want to extend it to A and to B and N, but that's not also so easy because what I did for the minimum supergravity, the important thing is that I imposed the strength into a supersymmetric invariant. But if you do 2A to B, you have both parallelities, and then it's not so clear that it's invariant. So it's not so obvious how to extend what we did to 2A to B, but that again requires more work. And theory, the bosonic sector has been done by these people, but the only thing is that the strange thing is that in step 1 of the paper, they already violate the rule of the invertible redefinition. They use extra fields, which later have something to do with the dual of the T-form field, but then it's not invertible. So either they could avoid unnecessary supergravs, or there's something funny going on, but I have to think about it. We have to discuss this there. This, by the way, is shortening of the knot that tries for a superspace approach. So always say that if you have a supergravity model, let's set case 0, then you get a smaller knot back. But that would be nice to understand also from the superspace point of view. In the talk, I forgot to state this mostly closed strings I did. There's also discussion open strings, which you can find a nice view by Z down. At this school we organized together with Niels and other people in the end of August, and it's very nice on the internet, so you can really listen to these lectures. I really recommend it, it's very useful. And also interesting connection with dome field theory, which is kind of alternative way to make these actions. It looks interesting. So in other words, there are many things to do. So but I think the message I want to give to you is that what this work made possible is that we introduced a kind of target space approach to field theory, which means that we can now apply many of the field theory techniques which we have used in the relativistic case in the past to get information about the non-behavior of string theory. You can now do in the relativistic case. The road is open out to to look clean for Brain solutions. For that, you need these T-duality rules. Also, compactification you can do. And so you can see that you can extend to all these Brain solutions, and then you really could start addressing the question: is there some sense to make out of the non-relativistic? Yes or no? And independently as yes or no, at least you can try to answer the question. You can see are the problems or not. So there are many interesting things to do using field theory techniques. That's what I want to say, and well, that's all I have to say.
Can you explain more on the rest?
On the Brain solution, yeah. Well, can I also talk about things you don't understand? Or?
Yes, of course.
Because I already, in fact, I already worked 2 years ago on Brain solutions, but it's first of all, the reason that we never published is that we have to understand first the T-duality first, because I use now extra bosonic constraint in the supergravity model. So to check something is a Brain solution, I have to check that the geometry constraint is satisfied. The puzzle is that you see in the relativistic case, if you look at the very basic ones, you have a wave and you have a fundamental string. And the wave becomes a string, and the string becomes a wave in the T-duality. Now here, in the non-relativistic case, you expect a string but not a wave, because usually there are no waves, there are no momentum modes. I forgot to say that with Groningen and Newton just mentioned, I think, by Niels, they only have winding strings, they don't have waves, which there are no waves in non-relativistic. But nevertheless, if you look to the T-dual side in relativity, there is a wave and there's a fundamental string, and they have a null direction, so you could determine the T-duality. And then the wave seems to give a string, but the string also seems to give a wave. But the funny thing is, it's a wave not in the transverse direction, it's a wave traveling along the string. So it looks like, this is all. So in other words, although they say there are no momentum modes, and that's probably there are no waves in the transverse direction, there is a kind of wave along the string. Somewhere that doesn't occur in the spectrum. So I don't know what it is important, because if you want to see what the duality symmetries are, then in the relativistic case, this leads to in Z2 leads to an SO11 symmetry. So if I lose a solution, I get less T-duality symmetries. So it's important that if I want to preserve all the usual T-duality symmetries, I really want to have two. So there's a clash between on one side, two solutions or one solution. I don't know the answer.
But doesn't it show that you cannot preserve all T-duality symmetries?
Say it again.
Isn't this in direct conflict with T-duality?
Well, if you expect no violation of T-duality, I would expect in my dimensions two particles which are
Why you wouldn't expect the violation of T-duality?
Well, because the in the relativistic case, there is no over one T-duality. The question is, what is the T-duality of the non-relativistic case? All I'm saying is that is it over one or less? Because I need two symmetries. I need two zero plates which are in a vector of the T-duality. That's it in the relativistic case. Because the wave and the string both give a zero plane in 9 dimensions, and they form in fact two-dimensional vector. But the question is, do I have now? Of course, usually people say the non-relativistic there's a string but no wave. But if I reduce that, then I get. So I like a wave, but I told you this is something I'm still.
A simpler question: do you expect that the full string spectrum in the non-relativistic string will exhibit the duality or not?
In the flat case, the statement is that there is a duality invariance in the spectrum. Yeah, and the spectrum is only winding string. That's the official statement in the original paper by Gomez and Guru. Yeah. Now I'm trying to understand it from target from Brain solutions. I'm just trying to understand the statement from the point of view of Brain solutions. And this I do not fully understand.
One comment about the wave on the longitudinal direction. In a sense, this is fake, because if you do the static gauge, you usually do that the longitudinal directions are the worship coordinates, therefore, in a sense, that is a gauge artifact.
No, it could be, although it's funny, because the original, before T-duality, it was the fundamental string of the other one. So, maybe you're right. It's just that I have not carefully investigated.
So, right? It's free parameterization.
Again?
I mean, the wave of a longitudinal direction cannot be physical.
Well,
it doesn't sound physical, right? Because
maybe it's not. But on the other hand, the one before T-duality was just fundamental string solution. That's super physical. So it's a bit funny. that the T-dual is not visible, but maybe you're right. And it's just that I'm not saying that here maybe it just doesn't fix. That's why we have to think a bit more. And yeah.
But this duality is curious. In the flat case, in the spectrum of Jaume and Woody,
Yeah.
they were passing from the non-relativistic string to a relativistic DLCQ relativistic thing. Therefore, there are
Well,
a few. That's funny.
Well, can I say this again? Something which I didn't fully understand and I'm embarrassed. It's very strange because if I follow my own story, then what I get is geometry to the null killing direction, and that is non-relativistic. So it's and I can obtain by a limit I showed. So in other words, it's a corner of relativistic C-field. But somehow people hook this on. They start talking about discrete lightning quantization string, which I purposely didn't mention. But then it's supposed to be a non-perturbable description of string fields more. So how can it be that on one side we want to present something as a corner of relativistic string theory, and now people relate it to something which is supposed to describe a non-perturbable fermionic string theory? This is probably my mistake that I did not fully understand it. That's why I didn't mention there was a whole lot of discrete lightning quantization. But there's something I don't fully understand. Yeah, because we are supposed to be doing that's the original purpose to see that it was a more simple corner of string theory. So it's funny, the same thing. Now, but indeed, that's what people say that the non-string may increase full description, blah blah blah. Yeah.
Okay.
But it's that the point, I mean, the matrix model.
Yeah, the kind of matrix
On the one hand,
zero planes.
looks like a non-relative limit of a theory, relativistic theory of the zero, non-relativist limit.
Yeah.
On the other hand,
Constant cancel it.
it is the
Yeah.
answer of the relativistic.
Yeah. Yeah.
And
But
you
it's
don't
not
have to take any limits at all. You just
Yeah. Yeah, but that's more or less than the story they tell you. But it's not part of my blood. But yeah, you're right. That's what people used to say. That's also in the work of Bernard the description of the Superman thing. Yeah. But it's funny that somehow, yeah. But yeah. But I didn't dare to mention it in my talk. Sorry.
No. Any questions? No, in internet there are no questions. You can see the chat here.
2 million people watching this seminar.
No,
Yes,
there was one. There was only one in internet.
There's one question.
No questions. One person. One person.
Not the whole universe, but only
Not the
one
whole
person.
universe, but that's fine.
All 10 million people have no questions. Okay. Okay.
Very well. Thank you very much. Sorry about this thing. I was leaving it.
Still,
This is it. Yeah, I think so.